Hey guys, I am in my living room recording. That's Eli. We're going to talk about conservation of mass and what happened in your lab yesterday. Oh, there's Evie. Everybody say hi.
Hi.
All right, we're going to talk about what happened in your lab yesterday. So, the conservation of mass is also known as the conservation of matter. You can, for these purposes, use those two words interchangeably.
I'm Spider-Man.
And what that means is that mass cannot be created or destroyed. This is a scientific law, which means that this concept will hold true no matter where in the universe you are, right? I can be on Mars, I can be in Pluto, I could be outside of this solar system. Mass cannot be created or destroyed. Now, if you are talking about black holes, that is an entirely different situation. If we are talking about moving at the speed of light, that is also a different situation. But for our everyday life, for all of the stuff that you do around you every day, mass is not created or destroyed. Which also means that matter or atoms are not created or destroyed. So during chemical reactions, whatever you start with has to be what you end with, because it cannot just disappear. Can't happen. So I hope that you guys saw that in your lab yesterday when you did it at home. When you mixed the baking soda and the water, vinegar, that the total mass stayed the same both before and after. Because what you started with, combined together, should be what you end with. Before we can talk about how this is practically applied. Okay, so this is practically applied when we talk about balancing equations and what all those numbers mean. But in order to understand what all that means, we have to talk about it. So a reaction, if you remember, is when we are creating something new and different from what we started with. So we represent this by using balanced chemical equations. An example of one is here. This is hydrogen, oxygen, and they will react together to make water. This right here is called a coefficient. It's the big number in front, and it tells you how many of these you have. Okay, so this is a coefficient. It's a big number. Tells you how many of this whole thing that you have. So if I put 2 here, it means I have 2 H2s. When there's nothing, that means that there's only 1, so you assume a 1. So because there's no number here, we just assume that I have 1 O2. Everything that I start with, so everything on the left side, are what we call reactants, and everything on the right side are the products. These little numbers right here are called subscripts, and those tell you how much of a specific element you have. So because I've got a 2 here, it means I have 2 H's that are bonded together. This does not represent a bond. It represents like me having 2 Oreos. That filling in the middle is what's holding my 2 cookies together. That would be the bond, but I would have 2 whole Oreos. Okay, this 2 right here means I have 2 oxygen atoms bonded together. And on this side, it means I've got 2 hydrogens and 1 oxygen all bonded together. So remember, reactants are what you start with. Products are what you end with because they're what you're producing. Now we need to talk about the type of reactions that we have. There's many different types, but there's a couple basic types that I'm going to go over and give you. So the first one is synthesis. It's like the reaction that we just saw. It's when you're creating something new and different from 2 elemental parts. So I've got hydrogen plus oxygen are going to be combined together to form water. Decomposition is the opposite of synthesis. I'm going to start with one compound and then break it apart into its elemental parts. So here we've got magnesium oxide that's being broken apart into magnesium and oxygen. Single displacement or single replacement, the displacement or replacement are interchangeable, you'll hear me use both, are when you have one compound with one element, and that single element will take the place of one of the elements in the compound. So in this case, the oxygen, because it tends to form an anion since it's a nonmetal, will take the place of the chlorine, which is also an anion. So this oxygen will kick out the chlorine and form sodium oxide on this side and chlorine by itself. Double displacement is when two things will switch places. It doesn't matter if the front, the cation, switch places, or if the back, the anion, switch places. The end result will be the same. I usually just switch the anions, but again, end result is the same. So in this case, we've got lithium bromide plus the magnesium oxide. The oxygen and the bromine are going to flip places to give me lithium oxide and magnesium bromide. We are going to stop here today and talk about balancing equations tomorrow. Please comment and let me know if you have any questions.